Once you have a good grasp of writing a linear equation in slope y-intercept form, you can determine the point where two lines intersect. By the end of this video, you will be able to identify a point of intersection from a graph and determine the number of solutions. And you will be able to plot linear systems onto a graph and determine and evaluate the point of intersection. A linear system is a set of two or more linear equations that are considered simultaneously or at the same time. So what that means is that you could take two linear equations and plot them onto the same Cartesian plane or the same grid. Once you've plotted them, you can see if and where those two lines intersect. If they do intersect, the point at which they do intersect is what we call a point of intersection. And sometimes this can be abbreviated as simply POI. A linear system could have one solution, no solutions, or infinitely many solutions. So let's take a look at each of these three scenarios. If a linear system has one solution, or what we call one unique solution, that means that your two lines will intersect at one particular point, or one point of intersection. Now, what's special about the lines that make up this linear system is that the lines will have different slopes and they will have different y-intercepts. So the two equations that make up your linear system, they will be completely different from one another. In order to have one unique solution or one point of intersection, your lines must cross or intersect with each other. And that means that if they are crossing, you are only crossing or intersecting at one particular point. Another situation is when you have two lines plotted on the same grid, but they do not intersect or cross each other at all. This creates a linear system that has no solution or no point of intersection. Now, what's special about the lines in this type of situation or scenario is that the equations will have the same slope, but they will have different y-intercepts. Now, we know that lines that have the same slope will be parallel, which means that they are lines that run in the same direction, and because of this, they will never meet, they will never cross each other, they will never intersect. So because they will never intersect, there is no solution, meaning there is no point of intersection. The third situation is a system where there is an infinite number of solutions. Now, if you look at the visual that's provided here, it only looks like there is one line plotted on this Cartesian plane, but in fact, there actually are two lines, and they are telling us here that line 1 is equal to line 2. So that means that the equations are exactly the same. They have the same slope and they have the same y-intercept. So it's like plotting the same equation twice on the same grid, and because the equations are identical, exactly the same, they're just going to overlap each other. One's just going to go directly right on top of the other. So because the lines overlap, all of their points are in common. So we can therefore say that there is an infinite number of solutions. There are infinite places where these two lines are intersecting because they're the same. They're just one, it's just one line on top of the other. So let's start with something very simple. We're going to take a look at two different linear systems. So we've got grids where we have two linear equations plotted together on the same grid. And we're simply just going to identify where the point of intersection is, and we will give the coordinates for that point. So in the first graph, we see that we've got a line plotted in blue, a line plotted in red, and the point of intersection is going to be where these two lines intersect or cross, and that is where my little pointer finger is pointing to right now. So this particular point is going to be our point of intersection, and to identify it, all we need to do is identify what is this particular coordinate point. So remember, a coordinate point is always made up of an x and a y value. So at this particular point, my x value is 2, and my y value is -3. So when we write our answer for our point of intersection, you can simply just write POI, which stands for point of intersection, equals, we'll create a set of open brackets for our coordinate point, and then we'll put in our values of 2 and negative 3. So here's another example where again we've got two lines intersecting each other. We can see very clearly that the lines intersect at this particular point. So all we need to do is identify the coordinates. So the x value of this point would be negative 2, and the y value would also be negative 2. So we can state that the POI is equal to negative 2 and negative 2. In our second example, we're asked to graph the following lines: y equals 1 over 3x minus 3 and x plus y equals negative 1 on the same grid, and identify the coordinates of the point of intersection. And then to follow up, we're asked to verify that our solution satisfies both equations. So this is a good question because it kind of incorporates everything that you should already know about equations or linear equations in slope y-intercept form. So it's going to be testing your knowledge of identifying things like slope and y-intercept, seeing if you can plot linear equations using slope y-intercept method on a Cartesian plane, and then identify a point of intersection. So before we go ahead and plot our equations, the first thing we want to make sure of is that both of our equations are in y equals mx plus b format. So when I take a look at my equations, the first one is very clearly in the correct format, y equals mx plus b, but my second equation is not. So the first thing that I want to do is take this second equation and rearrange it into y equals mx plus b form. So I've gone ahead and recopied that equation. The only thing that I really need to do here is take my x term and bring it over to the right-hand side. And so if I do that, that's going to leave me with y equals negative x minus 1. Now that we have the equation in the correct form, let's go ahead and identify our slope. Remember that your slope is going to give you the directions in which you need to move on your Cartesian plane. So from my equation, I can see that my slope is negative 1. And so I know that if my slope is negative 1, I can also express that as negative 1 over 1. So the top number, or the numerator of my slope, is going to represent my rise. And because I have a value of negative 1, that's going to tell me that I need to move 1 unit down. And my denominator, which is a positive 1, is going to tell me that I need to move 1 unit to the right. In order to start graphing, I'm going to start by identifying my y-intercept value. So in my equation, my y-intercept is negative 1. So on my grid, I'm going to go ahead and go to my y-axis, and I'm going to look for the number negative 1. Once I find that, I'm going to go ahead and place a point on negative 1. Once you've placed your first point on your y-intercept, you can go ahead now and use your slope directions in order to generate a few more points on the line. So from my y-intercept, my slope tells me I need to move 1 unit down and 1 to the right. So I'm going to go 1 unit down and over 1 to the right. So that takes me to a point of 1 and negative 2, and that's where I'm going to go ahead and place my second point. Remember, you should always try to plot at least 3 points on your line, so we're going to repeat the same process one more time. So from my second point, I'm going to go 1 unit down and 1 unit to the right, which takes me to a point of 2 and negative 3, and I'll place a third point there. Once you've plotted your points, you can go ahead and join them together with a straight line. So here is the line for the equation y equals negative x minus 1. Now because we are going to be plotting two lines on the same grid to find the point of intersection, a good suggestion would be to label your line, and I went ahead and labeled my line with the actual equation for this particular line. Now, the other equation in the system was the equation y equals 1 over 3x minus 3. So we're going to follow the exact same process to graph. Let's first start by taking a look at our slope. This time we have a slope of 1 over 3. So a slope of 1 over 3 tells me that I need to move 1 unit upwards, since my numerator number, my rise value, is a positive 1. And in my denominator, I have a 3, which tells me I'm going to move 3 units to the right. My starting point is going to be placed on my y-intercept value of -3. So let's go ahead and head over to the same grid that we used before. And again, you're going to start by going to your y-axis and finding your y-intercept value. Ours happens to be -3 this time. So I'm going to place my first point on my y-intercept value of -3. Now, my slope for this equation tells me I need to move 1 unit up and 3 units to the right. So from my point, I'm going to move 1 unit up and 1, 2, 3 units to the right. That takes me to a point at 3 and 2. So I'm going to go ahead and place my second point there. And I'm going to repeat one more time. So from my second point, I'm going to go 1 unit up and 1, 2, 3 units to the right, which takes me to a point of 6 and -1. So I'll go ahead and place my third point there. I'm going to join my points together with a straight line. So here are the two equations graphed together on the same grid. And just like I did before, I went ahead and labeled my line with the appropriate equation right next to it, so I know which line represents which equation in the system. Another tip when you are graphing two lines together, you want to make sure that you don't make your dots so super large, because as you're going to see when we talk about our point of intersection, we have something that is intersecting and it's not at a very concrete corner or grid point. So you want to be able to read off of your scale and off of your graph as accurately as possible. And you also want to make sure your lines are drawn as accurately as possible. So huge bubbles or huge dots are not really necessary. Just a small point or a small dot that you can use to simply connect your points together with a straight line. So we can see that these two lines clearly intersect at a very specific point, which is located right over here. So all we need to do now is identify what is this point of intersection. So if I go ahead and read upwards to my x value, that's roughly about 1.5. And if I read my y value, I could say it's roughly about -2.5. So we're going to write out our point of intersection as 1.5 and -2.5. Part B asked us to verify that our solution satisfies both equations. This is just a fancy way of asking you to take your point of intersection and check that it will actually work out or make your equation equal to what it's supposed to be equal to. So you're performing a check. Now, if you've never seen a check before, this is where you want to check that the left side of your equation will be equal to the right side of your equation if you were to take your x and y values from your point of intersection and stick them into the proper place in your equation. Now, they ask us to do it for both equations, so I'm going to show you how to perform the check for one equation at a time. So I went ahead and recopied the very first equation that we worked with, which was y equals -x minus 1. The next thing I did was right underneath my equation, I created a t-chart. So I've got two columns. One column I labeled as LS, which stands for the left side of my equation. So that's everything that's on the left side of my equal sign. And my other column I titled as RS, or the right side. So it represents everything on the right side of my equation. I like to think of the bar running down the middle as kind of like the halfway, or where your equal sign would be located. So in my left side column, I have the letter y, because the y is on the left-hand side of my equation. In the right side column, I'm going to copy out -x minus 1, since that is what is located or found on the right-hand side of my equation. Now, in terms of what I'm going to substitute in the places of the letters y and x, I'm going to go to my point of intersection and pick out my x and y values. Now remember, our point of intersection was 1.5 and negative 2.5. So my y value was negative 2.5. So I'm going to fill that in here. And my x value is 1.5. So we have to just be careful here. We've got a negative sign, and then we have our x value. So I'm going to go ahead and put in 1.5, and we still have a minus 1. Now, in terms of the left-hand column or the left side column, there is no math or kind of mathematical operation to perform. All I have is the number value negative 2.5. So I'm just going to go ahead and recopy that. But on the right-hand side, or in the right side column, we do have some math to simplify or calculate. So we have negative 1.5 minus 1. Now, negative 1.5 minus 1 is negative 2.5. Now, this is what we are looking for. We're looking to see that if we were to take our point of intersection, plug it back into the equation, you want to see the same number appearing on both the left side and the right side. This is verifying that that point of intersection satisfies this equation. Okay, so to conclude, we're going to simply state that the left side is equal to the right side. Put a little check mark if you like. That signifies or verifies that this point of intersection is good to go in this equation. We need to do the exact same thing, but sub in our point of intersection into our second equation that we worked with, and that was y equals 1 over 3x minus 3. So same like before, I recopied my equation, I set up my little t-chart and divided it into left side and right side. On the left side of my equation, I only have the letter y, but on the right side of my equation, I have 1 over 3x minus 3. So just like we did in the previous equation, we are going to take the x and y values from our point of intersection and plug them in. So the y value for our point of intersection was negative 2.5. And for the right-hand side, we need to plug in our x value, and our x value was 1.5. So again, on the left side column, or in the left side column, we don't have any mathematical operations to perform. We just have the numerical value of negative 2.5. So I'm just going to go ahead and recopy that. On the right-hand side, we've got 1 over 3 multiplied by 1.5. So I'm going to go ahead and do that with a calculator. 1/3 times 1.5 is simply 0.5. Still have a minus 3. I'm going to extend my column a little bit here. On the left-hand side, again, you're going to just recopy negative 2.5 on your next line. On the right-hand side, we're going to do the math. 0.5 minus 3, which gives you negative 2.5. So again, we can see that we generated the same value on the left-hand side as the right-hand side, which tells us that the point of intersection also satisfies this equation. So to conclude, we can say that the left side is equal to the right side, which tells us our point of intersection is good to go. There are many different types of application questions or word problem, thinking type questions that can be solved and be based around finding a point of intersection. So in this particular example, we are going to not only identify a point of intersection like we've seen before, but we're also going to interpret what that particular point of intersection means. In this example, Shane has a choice between 2 jobs helping people around his neighborhood. So he's got job option A, where his total pay is shown on the grid below, and I'm going to scroll down to the grid in a second. And he's got job option B, where Shane will receive a base pay of $30 plus $12.50 per hour. We're asked to determine the conditions under which Shane should select job A and the conditions under which he should select job B, and we're asked to justify our answer. So we need to give proof or explanation as to why he should choose one job or when he should choose one job over the other. So before we begin doing anything else, let's actually take a look at the graph that they have given to us. So they've labeled everything really nicely. We've got total pay versus the number of hours worked. So on our x-axis, we have number of hours worked, and they've chosen to use the letter N to represent number of hours. So rather than using X in our equation, we're going to replace it with the letter N. And on our y-axis, we've got total pay measured in dollars. And again, instead of using the letter Y, they've chosen to use the variable capital P to represent total pay. Another thing you might just want to take note of also is the scale that they've chosen to use, since we are going to be working with our graph and with a particular slope. So on the x-axis, we are skip counting by 0.5. So we've got 0, 0.5, 1, 1.52, and so on and so on. However, on the y-axis, they are counting by a totally different scale, and they are actually skip counting by 5. So again, we start at 0, and then we've got 5, 10, 15, 20, 25, 30, and so on. So it's completely possible to create your own graph where your scales are different on the X and Y. They don't always have to be counting by the same scale, but it's always really important that you take note of what a particular scale is if you are given the graph already. So like they stated, they took information about job A. They didn't tell us really anything about it in the question, but they said that they took the information about the total pay for job A, and they've plotted it for us on this grid. Now, if you really wanted to, you could go ahead and figure out what the equation of this particular line is. We don't necessarily have to, but if you really wanted to, you would already know what your y-intercept is. This line intersects or touches the y-axis at 0. Okay, remember, you can also look at it as what is the initial value of your line or your graph, and our initial value of this particular line is 0. The line starts at 0, 0. Now, if you wanted to find the slope, you could go ahead and pick 2 points, any 2 visible points on this line. You could draw a triangle between them and calculate or count out the rise and the run and figure out the slope that way. Or you could read 2 coordinate points off of this line and use your slope formula, y2 minus y1 over x2 minus x1, and calculate out the slope that way. Now, part of figuring out which conditions Shane should look at whether or not to choose job A or job B requires us to plot the information about job B onto the same grid and figure out or if these 2 lines will intersect. The place at which they intersect is going to help us make that decision on whether he should choose job A or job B. So the first thing I think that we should do is to take the information about job B and use it to build a linear equation. Once we have the equation, then we can take a look at how we can plot it onto our grid. Now remember, because we are talking about a linear equation, we need to build an equation that follows the template of y equals mx plus b. So let's go back to our question and take a look at the information that was given to us. So we were told that Shane would receive a base pay of $30. Now, base pay is just another term that could interchangeably be used with some of the other values that you've seen in other word problems, things like fixed value or fixed cost. So what that means is that even if Shane doesn't work any hours, this job will still give him a pay of $30. So this base pay is actually going to be substituted, or it's going to replace the letter B. The $12.50 per hour is our variable rate, okay, because this amount of money that he earns is going to change depending on the number of hours that he works. And remember that a variable rate or a variable cost can be used to represent your slope, or remember, this is also a rate of change. It is the amount of dollars that he's earning per hour. So I went ahead and put those values into my equation template. So my M was $12.50 and my B value was 30. But remember that this particular question had already picked out variables for you to use in the place of x and y. So I'm going to go ahead and switch those out. So instead of the letter y, they used a capital P. And instead of the letter x, they used a lowercase n to represent number of hours. So this is the equation that is going to model job B. P equals 12.50n plus 30. Now, in order to graph this equation onto our grid, we could go ahead and try to graph it the way that we did in our previous example, where we went ahead and marked our first point on our y-intercept value, and then we used our slope to give us the directions to move on the grid. The only issue here is our slope. 12.5 is not the greatest value to use when you're trying to skip count up and across or down and across your Cartesian plane, especially because our y-axis on our particular graph, it was already chosen for us and they chose to count by fives. So to skip count by 12.5 on a scale that's already counting by fives is not going to be very accurate, and you are more likely to make a mistake trying to do it that way. So instead, what we're going to do for this particular question is we are going to generate a table of values. So we're going to calculate the exact points that we want to plot onto our grid. So to make a table of values, you're going to make yourself a little T-chart. Normally you would label your columns as X and Y, but remember we're not using the letters X and Y because different variables were chosen for us. So in my first column, instead of an X, I'm going to use the lowercase n that they chose for number of hours. And instead of a Y, I'm going to use the capital P that they chose to represent total pay. Now, if you really wanted to, you could also write out the actual labels. So instead of N, you could totally write out the entire phrase, number of hours or number of hours worked. And instead of the capital P, you could choose to write out the phrase total pay. Now, I see that on the number of hours worked axis, remember they were counting by 0.5. So if you really wanted to, you could choose to skip count by 0.5 in your column for number of hours. But let's just keep it simple. We'll avoid using the decimal numbers. And I'm just going to focus on using whole number values in my column. So to calculate total pay, I'm just going to take my n value and substitute it into my equation. So if Shane works 0 hours, we're looking at 12.50 multiplied by 0 plus 30, which would give $30. And we're going to continue this pattern all the way down the table. So I continued my pattern all the way down. I actually added in another row for 5 hours, and now I'm just going to go ahead and calculate the total pay. So for 0 hours, we'd get $30. For 1 hour, it would be $42.50. Remember, since we are talking about money values, make sure that your answers have 2 decimal places on the end. If we are talking about 2 hours, that would be $55. For 3 hours, that would be $67.50. For 4 hours, that would be $80. And for 5 hours, that would be $92.50. So these numbers are going to represent coordinate points that we can now plot onto our grid. So we have our first point located at 0 and 30, and then our next point at 1 and 42.50, 2 and 55, and so on. So I'm going to go ahead and take all of our coordinate points, plot them on the grid. I'm going to connect them with a straight line, and then we'll take a look at what we get. All right, so here's a little bit of a zoomed in, closer look at our graph. I went ahead and plotted all of the points that we came up with for job B. join them together with a straight line. Now remember that you want to put an arrowhead on the end of your line and also label your line. So because they labeled the first line job A, I went ahead and labeled our second line as job B. Now we had a really clear and specific point of intersection, which was nice. It wasn't a weird decimal value that we kind of had to interpret and read off of the graph. We had a point of intersection located at the point 4 and 80. So I'm going to go ahead and label that directly on my graph, just so we don't forget. So our point of intersection is at 4 and 80. Now we actually need to use this point to help us answer the actual question, which is under what conditions should Shane choose job A, and under what conditions should he choose job B? Now when you are answering questions that ask you for conditions like this one, you are always going to have 3 answers or 3 points as part of your justification. The 3 points that you're going to come up with are going to be based off of your x value of your point of intersection. So for us, our x value was the number of hours, and in our point of intersection of 480, our x value or number of hours was 4. So using that information, I've come up with these 3 conditions. If Shane works more than 4 hours, if Shane works less than 4 hours, or if Shane works for exactly 4 hours. So dependent on these 3 conditions, that's going to determine whether or not Shane chooses job A or job B. One is going to be better than the other, or maybe they will be the same and there will be no difference. So now that we have our 3 different conditions outlined for us, we're going to go back to the grid or the graph, and we're going to take a look at how do we figure out which job is better. So let's take a look at what happens if Shane works for more than 4 hours. So we have our point of intersection marked for us here. So this is the point 480. And what happens if Shane works for more than 4 hours? So if we were to compare the line for job A to the line for job B, we would very clearly see that the black line representing job A is slightly steeper or more slanted than job B. And what this implies is that after 4 hours, as the time increases, so as if Shane works more than 4 hours, he will actually get more pay or more total pay for job A than he would for job B. So if he were to work for more than 4 hours, job A would be the better option. So if we go back to our conditions, I've written in my answer. If Shane works more than 4 hours, he should choose job A, where he would earn more money. Now let's take a look at our second condition. And our second condition was, well, what if Shane worked for less than 4 hours? So maybe he doesn't really want to work a lot, and particularly if he were to work for less than 4 hours. So again, we're going to go back to our point of intersection, but because we're talking about less than 4 hours, we're going to focus on the bottom half of the lines. Now this time, if we are working less than 4 hours, the red line, which represents job B, is slightly more steeper or slanted than the line representing job A. So this tells us that if Shane were to work for less than 4 hours, he would actually earn more money if he were to work or choose job B. Another way that you could also look at it or interpret it is that the line that represents job A, which is the black line, it is under or lower than the red line, which represents job B. So because the line for job A is lower, that also implies that he's making less money. And so obviously Shane wants to pick the job where he's going to earn the most money possible. So that would actually be the higher line, which represents job B. So going back to our conditions, I've put in our answer and I've stated if Shane works less than 4 hours, he should choose job B where he would earn more money. Our third and final condition was if Shane were to work for exactly 4 hours. So no more, no less, exactly 4 hours. And at the 4-hour mark, Shane earns $80 for job A, but he also earns $80 with job B. So at the 4-hour mark, he earns the same amount of money for both job A and job B, so it doesn't matter which job he chooses. So when you are giving your final answer, you're going to say if Shane works for exactly 4 hours, he can choose either job A or job B, since he will earn $80 at both jobs. I think it's good for you to put in that actual amount rather than saying he will earn the same amount. You know what that actual amount is because you know what your point of intersection is. You know your point of intersection is 4 and 80. So you know that at 4 hours, he's going to make $80 at both of his jobs. So to quickly summarize, when we are looking at a linear system, which is two linear equations plotted on the same Cartesian plane, you are looking to see if you will have a point of intersection. Now, for a linear system, remember there are 3 different scenarios that you could see. The first would be a system with one solution, which means that the 2 lines intersect at one particular point of intersection. You could have a linear system that has no solution, which means that the lines are parallel, they run in the same direction, and they do not intersect or cross each other, which means that there will be no point of intersection. The third scenario is a linear system that has an infinite number of solutions, and this is because you are talking about or dealing with the same line or equation. So because you have the same equation twice, if you were to plot them together on the same Cartesian plane, the lines would just overlap each other and they would be touching or intersecting at every possible point on the line. When you are given an application question where you are asked to graph a linear system, find the point of intersection, and then interpret that point of intersection as conditions, remember that you always want to have 3 conditions listed in your final answer. One condition will be more than whatever your point of intersection value was. So in the question that we did, remember we said more than 4 hours. Your second condition will be a less than, so you are looking at something less than your point of intersection. And your third and final condition will be exactly at the point of intersection. And typically, always at this last condition, when you're talking about the point of intersection, it will be the same answer or the same value or the same cost or the same price, depending on whatever it is you're talking about in the question. It shouldn't matter whether you're choosing job A or job B or option A or option B. They will be exactly the same since we are talking about the exact point of intersection, which is where they meet.